Space is the fundamental counting principle, which is where we're going to start. We're doing perms and coms this unit, and then probability the next unit. Then after that's your next unit test. Okay? And then after that, we have a cumulative on the first 4 units. So we don't let them go away, because your finals on all of them. So you don't want that to just you don't want to forget the stuff you did in September. So here we have solve problems involving the fundamental counting principle. So here's my question. London is shopping for a sports utility vehicle. The dealer says that he has 3 different models, Bronco, Explorer, and Expedition, and that each model is available in 5 different colors, gray, white, black, and blue. Complete a tree diagram. Now, please pay attention, because you're going to go do a tree diagram soon, and you're all going to do it wrong. You are. It happens. And then I come over and I'm like, remember how we did it in class 3 seconds ago? And you're like, no, I don't. So trees normally grow up or down. They're more vertical, correct? The trees that we are going to do will be horizontal. So it's like a shrub, maybe. Call it a shrub diagram. Okay? So they're going to grow out to the side. So you have to always, the way you make a tree diagram, is you label the options on the top. So the options that I have here are different models and different colors, okay? So I put model along the top, color along the top, and then these are going to be all my different outcomes. You see that? So I label the top. Everyone's paying attention. I see some phones. I don't like phones. Wish I could burn phones. Or just make them go away for the time being. So, for the model, what you do... Oh, Matt. You're in class. So, we have model, correct? We're going to list our different models underneath the title model. So, we're going to list Bronco, Explorer, and Expedition, and we're going to leave a little space around them. So we're going to go Bronco, and then we're going to leave a space, and then we're going to go Explorer. If you don't leave spaces, you're going to regret it in about 3 seconds. And then our last option was Expedition. You see how I list the 3 options? In a row, under model. We agree? Now, in your next column, it's going to be color. You're killing me, Smalls. You're doing homework in my class? My homework? That's a problem. All right. In the next column, you're going to put color. The color options are gray, brown, white, black, and blue. So the Bronco can be in gray, brown, white, black, blue. And then the Explorer can be in what? Same thing, so I listed off gray, brown, white, black, blue. And then your Expedition is going to be in gray, brown, white, black, blue. So you see the first one I listed what the models were in order, gave spaces, then off those models I listed the color per each, correct? Then our outcomes, we're just going to list what they are. So our outcomes, we could have a Bronco in gray, or a Bronco in brown, Bronco in white, Bronco in black, Bronco in blue, and an Explorer in gray, an Explorer in brown, an Explorer in white, an Explorer in black, Explorer in blue, and then an Expedition in gray, an Expedition in brown, an Expedition in white, an Expedition in black, and an Expedition in blue. So using the tree diagram, it actually shows every single outcome, right? Every kind of outcome, yeah.
Do we have to write that word every single time?
If it was on a test, yes.
Like, could you not do Bronco one time and then do like the 2 dashes?
Nope.
Really?
If it was a test, no. You'd be assuming that people know what your dashes mean. You have dashes, the next person has arrows, the next person can't do assumptions. You have to draw the whole thing. Majority of the time, tree diagrams are not asked. This is just to explain why the fundamental counting principle works. So, don't fret, my pet. Okay. So this just shows all of the outcomes, and all of these outcomes being shown is helpful to us for probability, the next unit. For now, this is helpful to us to just show why fundamental counting principle works. So, if we look here, we have Bronco, gray, brown, white, black, blue. There's 5 of them. Explorer, gray, brown, black, white, blue. Okay. Expedition, gray, white, black, brown, blue. We agree? So how many outcomes are there total? London has? How many different outcomes? How many different choices? 15. Now, is there a way that I could do this mathematically quicker? 3 times 5. And the reason why I can do that is there's 3 models, and each of those models comes with 5 colors. Right? We agree? That's what the fundamental counting principle is. So here it says, look at the number of choices there are for the model and the number of choices there are for the color. How do we use these numbers to arrive at it? We do 3 times 5 because there's 3 model options. There's 5 color options. And that gets me 15 total options. The fundamental counting principle you can use when you have different parts that create the whole object. But you have to, like, if the expedition didn't come in all 5 colors, we wouldn't be able to use it, right? It has to be that there are 3 models, they all come in 5 colors. We agree, which gets us 15. So, the next one says, the dealer tells London that each of the SUVs comes in 2 editions now as well, SE and LE. How many different choices are there for her? Or that does she have? Up there it should have said her and it said he. So we have a model. How many different models are there? There was 3. Then we have the option of colors and color of how many options? 5. And now we also have to pick an addition. How many different options? How many different addition options? 2. When I multiply them out, how many options do I have? 30 options. And we can do this because when I go to this dealership, I have to pick a model, I have to pick a color, and I have to pick an addition. And when you use the word "and" in between, you multiply. We're going to write that as a little reminder for ourselves. If we use the word "and," we are going to multiply. So if I have a model and color and an addition, I'm going to multiply. If I needed a model or a color or an addition, I would add, but that makes no sense. You can't pick a model or a color. You just walk away with red. Like, here, I bought red. No, you didn't buy red. You bought red Ford Explorer or whatever in an LE option. So it was ands. Okay. So I'm going to get you guys to try. So here it says the fundamental accounting principle. We'll go over this first. The fundamental accounting principle can be extended to more than 2 tasks. If one task can be formed in A number of ways, another task in B number of ways, another task in C number of ways, A times B times C would give you the amount. And the word and is what you need for the fundamental accounting principle, and it means multiply. Now what I could be doing is I could be making Barbies, let's say, and you, for every single Barbie, you got to pick a certain number of hats, certain number of shirts, certain number of pants, correct? So I take however many options of hats times by how many options of shirts times by how many options of pants, and I would know how many different Barbie outfits I could make, right? So it's when you need all of those options. You have to pick something from this option, hats. You have to pick something from this option, shirts. You have to pick something from this option, pants. You can multiply them and get an answer. So you guys are going to try this one out. Your turn. It's dealing with a robot. Fill it in. Remember when you go to fill it in, you're going to have head as a title. You put your titles at the top, the different parts at the top. Because remember when you do fundamental accounting principle, you're going to have the different parts here. You're going to have head, body, and shoes. So when you go to list the tree diagram, you're going to go head, body, shoes. So the head is in red or blue. So you're going to go red, and then you're going to leave a really big space in blue because you're going to have lots of colors off of it. And then off of the head, you're going to have the body, which is going to be orange, white, and black. Orange, white, black. And you're going to do it again for the blue. And then for the shoes, you have purple or pink. So off here, you're going to have purple, pink. Because in the head option, you have 2. And in the body option, you have 3. And in the shoes option, you have 2. And do I need to pick a piece of the head, a body, and the shoes to make the full robot? Or head, or body, or shoes to make the full robot? It's going to be and or. Head and body and shoes? Or can I pick a head or a body and shoes? It's going to be and. If it's or, you have a head sitting in your hand. Is that a robot? Or you have a body sitting in your hand. Is that a robot? Or you have a shoe sitting in your hand. Not a robot. So I need to pick one of the options of head, and one of the options of the body, and one of the options of the shoes to get you 12 options, or 12 robot options. But you need to make sure you finish this off, so it's purple and pink. So just like with the fundamental accounting principle, you list your 3 blanks with the headings. Just like when you go to the tree diagram, you're going to list the 3 blanks with the headings, right? You do purple and pink. And then you could list the options for all of them. There will be 12 though, because it's going to be 1 option, 2 options, 3 options, 4, 5 options, 6 options, 7 options, 8 options, 9 options, 10 options, and then 11 options, 12 options. So you should have the same amount of number of options at the end, right? So do you see how I listed the titles at the top? And when I do fundamental accounting principle, I list the titles underneath. Do you see that? So it's the same option. So you guys are going to try number 2. Number 2 is a jersey, pants, and socks. So what am I going to do? I'm going to go jersey, pants, and socks. Jersey along the top, list my options with spaces. Pants along the top, off of that one. Socks, one little tick coming out as red. Okay? You guys are trying number 2. We're going to go, for the most part on the test, you're not even going to get tree diagrams. Tree diagrams are, though they are very helpful for probability though, because it might say, what's the probability in the next unit that he has an outfit with white pants? Well, then you can go through and you can actually count all the options with white pants and put it over the total, right? So a tree diagram is more helpful for probability when you want to visualize it. But for this unit, as long as we understand that the tree diagram gives you the fundamental counting principle, that's good. So we would have jersey, pants, socks, and I need to pick, paying attention, I need to pick a jersey and a pair of pants and a sock color, correct? That's why I'm multiplying. That has to be a big seller home to you. If I say the word and, it's multiplication. So I have jersey and pants and socks. So the jersey is 2 options. The pants I have 3 options. And the socks I have 1. Now, the number above represents the amount of options. The blank tells you how many of each I'm picking. So how many am I picking of a jersey? 1. Pants, 1. Socks, 1. And I get 6 different options. Right? Okay, we're going to flip over. Now, what's the probability of a color rush outfit? So it has to be the same colors, yeah? Yeah. So in the NFL, they have color rush days. And in the color rush days, you use the exact same color. So you'll look, their jersey, their pants, socks, everything will be blue. It's like their main color of all of their options. So for like example, the Denver Broncos would wear like all blue. The Colts would wear like a light blue, right? Yeah. Yeah. So how many options do they have the same color the whole way through? There's only 1, right? It's red, because the socks are red, so to get a color rush, you'd have to have red in the other 2, and the only option I have is socks is red. So it'd be 1 out of 6. So here's some diploma practice. Jeremy wanted to go shopping for pants to make sure he had enough different outfits. An outfit must have a shirt. I must have 1 shirt. Right? And 1 pair of pants. And some socks. Can I make an outfit with only like shirts and pants, or pants and socks, or socks and a shirt? Or do I need 1 of each? 1 of each. So I need this and this and this. So I'm going to multiply. And we don't want to repeat the same outfit for 48 days. So what must this equal? 48 for 48 different outfits, correct? In his closet, he has 8 different shirts. So he's 8 shirt options. And 2 different pairs of socks. So 2 sock options. So I need to figure out a value here that would get me 48, correct? So what's 8 times 2 is 16, correct? And 16 times what is 48? It's going to be 3. How else could I do it instead of multiplying? I could go 48 divided by 16 and I get 3. So how many different pairs of pants must he buy? 3. And then you can have different outfits. So here we have a math quiz consists of 6 multiple choice questions. How many parts are there to this test? 6. So I'm going to have question number 1, question number 2. Do I have to do both of these? 1 and 2? Do you always have to do 1 and 2? You give no options, right? You can't be like, I'm going to do 1, I'm not going to do 2. Do 3, maybe 4. Like, it's all ands, correct? I have to do number 1 and I have to do number 2 And I have to do number 3. And I have to do number 4. And number 5. And number 6. Each question has how many options? A, B, C, or D. How many options do I have? 4, right? So below here I could list, okay, I have the options A, B, C, or D. And then I list in here I have 4 options. We agree? How many would I have for number 2? 4. How many would I have for number 3? 4 and then 4. I have 4 options. 5, I have 4. 6, I would have 4. How this can change is I can say Mrs. Lepp had an answer sheet for the 6 questions on her test. 6 multiple choice questions on her test. Oops, she spilled her coffee on the paper and it washed away the bottom 4 answers. Okay? So if that happened, the first 2 answers would still be on the paper, wouldn't they? So how many options would I have for number 1 and number 2 in that example? I'd have 1. And I'd have 1. Why would I only have 1 option for the first 2 numbers? If it was a piece of paper and it washed away the last 4 answers. Are the first 2 washed away? Are the first 2 on that answer key washed away? No, so I'd have 1 option for the first answer. It would be whatever it was. You could see it. Say I bolded C. Then I bolded B on the next one. So for the first 2 questions, I only have 1 option because they were there. They're on the sheet, right? And then 3, 4, 5, 6, I'd have 4 options, 4 options, 4 options, 4 options because I didn't know what the answer was to those ones. Now for people who think they can guess and pass, it's not true. So this is just a 6-question quiz. This is just a 6-question quiz where I have 4 options for each, which means you have a random choice of picking 4 options, right? Let's pretend you absolutely know nothing and you're randomly guessing. Obviously that doesn't normally happen. You can normally narrow it down, right? But say we're randomly guessing. My answer is going to be 4, not times 6. It's going to be 4 to the power of 6, because 4 times 4, which is actually a large number.
40.
How much is it? 40,000.
96.
96?
No, 4096. 4096.
4,096? Should be larger than that.
No, that's what I put in.
Maybe it is. 4 to the power of 6. Still a high number. 1 in 4,096 chance. That's you still have a really low chance of getting 100%, right? Because there would be 1 correct answer key there, so you'd have 1 in 4,096 chance of guessing all of the answers correct on that 6 quiz. Okay, this one we're paying attention. These ones come up a lot. So how many odd? Let's go there first. Let's go to odd first. What does odd mean? How can we tell if a number is odd? Anyone have not divisible by 2 and non-divisible by 2? That doesn't help. How can we tell something is odd? Let's go like this. Ready? You tell me if it's odd or even. 2,675,402. Even. 90,764,768,903. Odd. What are you only listening for? The last digit, right? I could list 797 billion trillion 2. You're like, even. You don't listen to anything else I say. You get overwhelmed, then you're like, I'm not going to listen anymore. And then the 2 comes out, you're like, oh, even. You don't even realize why you picked that out so easy. It's the last digit that matters, right? So if I ask you for an odd something, that means, indirectly, the last digit must be odd. How many odd? 4-digit numbers. What does 4-digit numbers mean? What's a 2-digit number? 98, 75, 36, right? What's a 4-digit number? 3,420. There's way too many people on phones right now, which means you're not listening, which means you're going to do crappy. Okay? I don't want you to do crappy. So 4-digit numbers, 3,768 would be a three-digit number, right? Let's say I tell you I'm going to pay you in a 3-digit number, all right? And I'm going to pay you $320. What would you tell me? You tell me you are terrible. That's not a 4-digit number. What is that? That's actually a 3-digit number with a 0 in front, correct? So when it says 4-digit numbers, not only does it have to have 4 blanks, it has to have 4 blanks, which is true. What else does that mean? The first digit can't be 0.
It must be a natural.
Yeah, it must be a natural number. So, do I need all 4 blanks to make a 4-digit number? Yeah, I need this blank and this blank and this blank and this blank, right? I need 4 numbers to make a 4-digit number. So 1, 2, 3, 4. I give myself 4 blanks. And I'm going to do this one and this one and this one and this one. Okay? Have a 4-digit number, I need to have 4 blanks. We agree? Now, we have to do the restrictions first. What were my restrictions? The back number, if I want an odd 4-digit number, the back digit has to be the numbers what? 1, 3, 5, 7, or 9. Could it be 11? No, that's a 2-digit number, and each one of these blanks can only fit a 1-digit number in it, correct? So my back options are going to be, I always list my options below and then how many there are above. So in the back digits I have to have 1, keep switching on me, let's try to make this. Has to be 1, 3, 5, 7, or 9. Those are my options. It goes away when it wants, it's really annoying. Okay. And then my other part that is restricted is what? The first digit can't be what number? 0. So it can be 1 to 9. Is there any restrictions on my 2 middle numbers? On my 2 middle blanks? Nope. They can be the digits 0 to 9. People forget that 0 is an option, but 0 is a single digit. So did I list all my options that I can have in each blank? Now I just have to list how many of those are above. So I have 1, 3, 5, 7, 9. How many of those are there? 1, 3, 5, 7, 9 is how many options? 5. I can deal with the restrictions first. 1 to 9, how many options is that? 1 to 9? It's 9. So I list a 9 above. So that's not the actual number on the above. Above it isn't. That's not the actual 4-digit number, is it? Am I saying that's what the 4-digit number is? No, it's just the options I have for those blanks. Just like when I had a jersey and it was 3 colors, I put 3 above, right? When I had socks and it was 1 color, I had 1 above. If it was pants, it was 4 colors, I had 4 above, right? So the number above the blank just represents how many options I have. Then 0 to 9 is how many options? 10. 0 to 9 is 10. So some people will say, how can I put the number 10 in a blank? That's not the number, right? That's how many options it is. We agree? So this represents 9. I have 9 different options for the first blank, 10 different options for the second, 10 for the third, 5 for the fourth. And how many is that? 4,500. Yeah, 4,500. So how many odd 4-digit numbers are there in the world? 4,500, right? Different odd numbers. Now this is the next one. This one here is the one that gets people paying attention. This one says how many odd 4-digit numbers. So that's still the same as the previous one, correct? Odd meaning last digit has to be odd. 4-digit numbers means the first blank can't be 0. Are there? But this is the catch. No repetition. No repetition. Ready? How many blanks do I need? 4. I have to deal with my restrictions first. So in the back blank, it has to be odd. So what options do I have? Same as before. 1, 3, 5, 7, 9. I have 5 options. This is where it changes. Are you ready? I said I can't repeat a digit. We agree? No digits can be repeated. So the way I do these questions personally, when it says no repetition, is you always start off with the restrictions first, which was the back and the front, correct? That hasn't changed. But I pretend to hold a number. I pretend to hold a number. So I'm going to pretend to hold the number 9. So I'm going to color it. I'm going to put a box around it. I'm pretending that I'm keeping the number 9 there. Do you see that? Could you have picked 1, 3, 5, or 7 as well? Yeah, you just need to pick one and box it when it says no repetition. That's the key thing. You have to keep a number and box it. So now I go to my next restricted number, which was the first digit. It could be the numbers 1 to 9, correct? It just can't be a 0. We agree? Can it still be the numbers 1 to 9? No, I boxed 9. It's out. If you boxed 1, 1 would be out. If you boxed 5, 5 would be out. If you boxed 7, you couldn't list 7. Does that make sense? I always box the furthest ones because it makes it easier for me to write things. So instead of having the options of 1 to 9 for this first blank, I actually only have the options 1 to 8. Because I boxed the number 9. Yeah. So I have 1 to 8. How many options is that? 8. If you don't know, you know what's sillier than using your hands, which people don't want to use their hands to count? You know what's more silly? A wrong answer. That's what's more silly. What's more silly is you don't use your fingers and you write a 9 or a 7 in that blank. That's worse. I would rather you go 1, 2, 3, 4, 5, 6, 7, 8 is 8 with my fingers and get this question right. That's not silly. Silly is you are too bold to use your fingers and you write 7 or 9 in that blank. Okay? Now I have to once again hold a digit. I'm going to be a rebel and I'm going to hold the digit 1 this time. So now which ones have I used up? Myself. I've used up the digit 1 and the digit 9, correct? So in the next blank, no matter what I want to write, I can't write 1 or 9 because I've used them up. I'm pretending, correct? If you picked 8 instead of 1, you would have used up 9 and 8 and you wouldn't be able to list those, right? So it doesn't matter what one you pick, you just can't list them in the next blank. So 1 and 9 are out. What can I put in these? I can't put 1 and 9. Is there any restriction on this blank? No, I had 0 to 9 last time, correct? The only catch is I can't have 1 and 9 this time because I'm holding them. And it says no repetition. So I could have 0. I can't have 1. I could have 2, 3, 4, 5, 6, 7, 8. How many options is that? It's 8. Now, why is it still 8? I got rid of 1 last time. Because I could bring the 0 back, right? I have to hold another one. I'm going to hold the 0. So what options do I have for this blank now? 2 to 8 I can write. Or I could say 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Just how many options? 7. And it should be 1 less than the original, than the one right before it, sorry, because I took just the 0 off, right? Now, do I multiply those numbers or add them? With the fundamental counting principle, what do I do? I multiplied, correct? And I multiply when I use the word and. We agree? Do I need this blank and this number and this number and this number to make a 4-digit number? Or could I just have this one or this one or this one or this one? I need this and this and this and this. And when I say and, I need to Multiply. When you multiply 8 times 8 times 7 times 5, what do you get? 2,240? So, there were 4,500 odd 4-digit numbers, correct? The moment I made them not repeat, I only have 2,240 odd 4-digit numbers, right? Because it takes away a whole bunch of other options. Okay. Example 4. Car number plates in an African country consist of a letter other than I or O. So a letter other than I or O. So I just go I, O, and slash through them because I'm just being lazy and I don't want to write A, B, C, D, E, F, G, H, J, K, L, M, N, P, Q, R, S, T, Z. Like, I don't want to list 24. Now the reason why people usually get this one wrong is because they forget there's 26 letters in an alphabet. If you forget, please count with your fingers. I don't really care. But don't put the wrong number. That would stink. Okay? So that's a restriction. So it has to consist of a letter other than I or O, followed by 3 digits. The first can't be 0. Followed by 2 letters which are not repeated. We don't care about the first blank. These 2 just are not the same letter. These 2 back ones can't be repeated. Okay, so they have to be different letters. Doesn't matter what the first one is. So these ones have to be like, for example, A to Z. And then this one would have to be A to Y, let's pretend. Pretend I held the Z. Right, when it says you can't repeat. So what's my options on the first one? I have to deal with the restrictions ones first. So these 2 blanks right here, I'm going to deal with last because there was no restrictions on them, correct? So I deal with the restrictions first. So this first blank can't be I or O. So how many options do I have? 24. Because there's 26 letters in the alphabet. The second blank can't be the digit 0, but it can be 1 to 9. So how many options is that? 9. And we multiply because we need this one and this one. Then I go to these ones because I have to do restrictions first. So this first blank can be A to Z, which is 26. And then it says I can't repeat, so I hold the Z. So now I have 25. Are there any restrictions on the 2 middle blanks about digits or anything like that? No. So they can be 0 to 9, both of them. And it doesn't say they can't repeat or anything. 0 to 9 is how many options? 10. So we're going to go 24 times 9 times 10 times 10 times 26 times 25, which is 14,040,000. That's a lot of license plates. So as an aside, we're not writing this down, just as an aside, our license plates, let's say. How do our license plates go? I go letter, 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 number, 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 right? That's how the basic old ones used to go. Letter, 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 number, number, number. So, you guys are just paying attention. They go letter, 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 number, number, number. Now there are restrictions on it, like certain blanks can't be certain letters and stuff like that, but let's pretend there's no restrictions, okay? So this would be letter, 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 number, number, number. So let's pretend there's no restrictions on it. I would have 26, 26, 26, 10, 10, 10. There are restrictions, but we're going to pretend there aren't any. So I go 26 times 26 times 26 times 10 times 10 times 10. And I get 17,576,000. That was the license plates. Now there's less than that because I told you there's some restrictions, right? We're not going to list them. So maximum with no restrictions, I'd have 17,576,000, right? But because there's restrictions, it actually knocks it down substantially. And what they were realizing is they were running out of license plates. Okay? Think about it this way. There's 4 million people in this province, 4.6 million or whatever. And some people own more than one car, right? Obviously, children don't. But some people also keep license plates and don't reuse the license plates. And we have restrictions, so we don't have that many, correct? So they realized, hey, we're running out of license plates. So what they said is, let's add another what? Remember what they added? They add another letter or another number? They added another number. So what they did is, and you're thinking, hey, adding another number wouldn't do much. But think about it. 26, 26, 26, 10, 10, 10, 10. What does multiplying by 10 add? Another 0. So that makes me go from 17 million to, add another 0, 170 million. Right? So add another 0. So that doesn't just like move it up a little bit. That trumps it up a lot. So some people would have said to me, well, why didn't we add another letter? Well, did we really need to multiply by 26 when 10 gave us a whole nother digit? Like it shoved it to the 100 millions instead of just 10 millions, right? So it does make a big difference. So that's why they added the 10. A reminder of the little idea of how we actually use it in our world. Yeah? Yeah. So what we're going to do is we're going to move ahead a couple pages. We'll come back to that. I'm going to get you guys, we're going to come back to those questions. I want to get you guys to do a few questions on your own. So you're going to try A, B here in the your turn. A and B. Just try those out for now. A and B. Now a 3-digit code. Can a code start with the number 0? Yes. Can a 3-digit number start with the number 0? No. So if it's a code, we can start with 0. The code could be 000, couldn't it? I would suggest that not be a code you choose, but it could be 000. So a code doesn't cause the first blank to not be a 0. A 3-digit number would, 3-digit code wouldn't. So you're trying A and B. Why is it so thick looking? Okay. So here we have a luggage lock opens with the correct 3-digit code. Key thing here is code as opposed to number. Matt, which one way? So each wheel rotates the digits 0 to 9. How many different 3-digit codes are possible? Then I can start with a 0. They could all be zeros. It's a code, not a number. So that would give me 10 times 10 times 10, which is 1,000. Then suppose each digit can be used only once. How does that change? Well, I could have 0 to 9 here, which is 10 options. Repetitions are not allowed, means I hold one of them. So now I could have 0 to 8, which is 9 options, hold one. 0 to 7, which is 8 options, which is 720. B says an Alberta license plate has 3 letters followed by 3 digits. For example, A, B, C, 1, 2, 3. The letters I and O are not used as confused with 1 and 0, which makes sense, right? So 1, 2, 3, 4, 5, 6. I need 6 blanks. I need this one and this one and this one and this one and this one. I need them all because I don't have an option of having less letters or more. In this case, I have to have 6. Now, the I and the O are not to be avoided with 1 and 0, so the only restrictions on these ones are that I can't have the digits or the letters I and O, correct? So I have to start with those first. Does it say anything about not repeating or anything else? No. So the only option I have is this one has to have 24 and 24 and 24. So I have to start with those ones first because I have to start with restrictions first. The digits have no restrictions, so I can go 0 to 9 on all 3 of these. So I go 10, 10, 10. I don't know what that gets. What is it? Do you have it, Maya? Do you have the number to that? Just read the numbers.
138 24000.
So it'd be 13,824,000, right? So that's still quite a drop from the 17 million we talked about earlier, right? Without any restrictions. Then, what's that? Do you have a different number? No? Okay. So then we have, because of growing number of vehicles, the province is changing the place with 3 letters followed by 4 digits. How many different plates are possible? So all that ends up happening, as you know, when we add a digit, is I just add another 0. So I'm going to get 130 million, 138 million, oops, 240,000. Okay, then we have Sally wants to decorate one wall in her room with movie posters. She will hang 5 of the 8 posters that she owns in a single row. She's hanging them in a single row. 1, 2, 3, 4, 5 of them in a single row. Does she have to put all of them on in the row? Does she have to hang 5, or could she hang 4? Or could she hang 6? Which she wants to hang how many? 5. So she wants to hang all of them, so we want this one and this one and this one and this one and this one. If Sally places her favorite poster in the middle, so this is the favorite one, then the number of different arrangements are possible. How many options of favorite does she have? It's her favorite poster. 1. So we have to deal with this one first, and she has 1 option, correct? Now she placed her favorite poster there, correct? It's placed. So how many options does she have for this first one? How many poster options? Nope. She had how many total? She had 8. She placed her favorite, so how many does she have? 7. Then she leaves a poster here, doesn't she? So how many does she have for this one? 6. Then she sticks the poster to the wall. How many does she have for this blank? 5. She sticks a poster to the wall, then she has 4. What's 42 times 20? 840? B. Then the last one. From 1951, don't pack up. From 1951 to 1981, the first digit of every 3-digit telephone area code in North America was 2 to 9 inclusive. The second digit was either a 0 or a 1. The last digit depended on the following rules. If the second digit was a 0, the last digit could be 1 to 9. If the second digit was a 1, the last digits could be 2 to 9. So we're going to do this one. It's 2 to 9 here, no matter what. If this is a 0, then this could be 1 to 9. Or we could have 2 to 9. If this was a 1, this could be 2 to 9. Digits could be used more than once. You're going to have to multiply and add. We'll go over it tomorrow.